So the formula that Euler discovered that ties together the number of faces, edges, and vertices of a plane drawing of a planar graph is the following. If you have such a graph, and if you assume that it's connected, so for now this assumption will be important, then the number of edges, vertices, and faces is tied together by this formula. Number of vertices minus number of edges plus number of faces is equal to 2. This applies for any plane graph. Another way to phrase this is that if you solve for f, the same formula is telling you that f is equal to m minus n plus 2. Now, m is the number of edges and n is the number of vertices, and these two numbers have nothing to do with planarity or plane drawing or something like that. They are just constants in the graph. You will not change the number of edges or vertices if you draw the graph differently. So saying that f is just a function of the number of vertices and edges and nothing else says that it is independent of how you draw the graph. So let's look at a few examples. The example we looked at previously was that of the graph K4. Remember, K4 has 4 vertices and it has 6 edges. And we saw from the way we drew the graph that it has 4 faces in the planar drawing we made, and indeed 4 minus 6 plus 4 is equal to 2. Another interesting graph or class of graphs are trees, as you all know. So if you have any tree like that, what possible faces can you have? Well, in order to have a finite face, you have to have something that is enclosed by edges. In other words, a cycle. Yeah, but trees don't have cycles. So this means that for any tree, the number of faces is always 1. There is just the infinite face, the void that the tree is helplessly plunged into. And as we have said millions of times, the number of edges in the tree is the number of vertices minus 1. So if you put these together, the n minus m plus f now becomes n minus 1 plus 1, and the n's cancel. 1 plus 1 is 2. So again, the formula holds for trees. I mean, obviously it holds for any graph, but we're checking the formula on these examples. So how would you prove Euler's formula? The proof goes by induction on the number of edges. So let us see how this works. The base case is the smallest possible number of edges. In that case, the number of vertices is equal to 1. Why is that? Well, we're assuming that the graph is connected. So if it has no edges, it cannot have more than one vertex. But in that case, G is just the null graph that has one face, the infinite face. And so the vertices minus edges plus faces formula is 1 minus 0 plus 1, which is obviously equal to 2. Now let's go to the induction step. So assume now that we are looking at a graph having some positive number m of edges, and assume that we know that any graph with fewer edges than that satisfies the formula. So this is our induction hypothesis, that Euler's formula is true for any number of edges smaller than n. So if our graph is a tree with m edges, then as we just saw, the number of edges is the number of vertices minus 1, and we only have the infinite face. So in that case, n minus m plus f, since this is n minus 1, the n's will cancel, and since this is 1, we get 2. So if our graph is a tree, we don't even need the induction hypothesis. The theorem holds. If our graph is not a tree, then since it is a connected graph, the only way it can fail to be a tree is if it has one or more cycles. So if it has a cycle somewhere, remove an edge from this cycle. If it has multiple cycles, just pick one cycle and remove an edge from that cycle. What do we know about our graph that results in this removing of edges? It's still connected because we've seen this before. If you take a tree and remove an edge, it will be disconnected. But if you have a graph where there is a cycle and you remove an edge from the cycle, it will not disconnect the graph. No bridge can lie on a cycle. So when we have removed this edge, since we haven't removed any vertices, the number of vertices is still the same. Obviously, the number of edges is one less because we have removed one edge. Perhaps less obviously, the number of faces has also shrunk by one. Why is that? Well, pause and think about it. So the reason is, if you have a graph like that, say, and if I now remove, so let's look at, so now I have a bunch of faces. So I have this red face and this green face, for example. And if I remove an edge, then it will merge together exactly two faces. So two faces become one. And the same if I had removed one of these outer or this outer edge, then the green face will have merged with the infinite face. So removing an edge merges two faces. Okay, so now I have a connected plane graph with this number of vertices, this number of edges, and this number of faces. And the important thing is this new graph has fewer edges than I started with. So since I'm using induction, by induction hypothesis, this graph will satisfy Euler's formula. So the number of vertices minus the number of edges plus the number of faces is going to be equal to 2, because the graph has less than m edges, and I am assuming the induction hypothesis. Okay, but then just I need to observe that minus minus 1 is plus 1, and this cancels this minus 1 here. And so we get n minus m plus f equal to 2, which was exactly what we wanted to prove for our original graph. And we are done. So the step from the induction hypothesis to the actual case is very simple. We just cancel out these ones. The important thing to realize is that the number of faces has been reduced by 1 when we remove an edge. So far we've assumed that the graph is not only planar but connected. What if the graph is not connected? Well, knowing Euler's formula for connected graphs, we can derive a similar formula for graphs that are not necessarily connected. And that goes as follows. So if you have a plane drawing of a planar graph, now not assumed to be connected, then the number of vertices minus the number of edges plus the number of faces is equal to k plus 1, where k is the number of components. So in the connected case, k was equal to 1, because a connected graph has one component, and we get back our n minus m plus f equals 1 plus 1, which is 2. So how do we prove this in general? Well, before we get to the proof, there's an important remark that will help us. And that is, if we have a plane graph with f faces, then it has f minus 1 finite faces. So we have seen this before. We always have the infinite face, and so the remaining faces are finite. If the graph is connected, then we have Euler's formula that says that f is equal to m minus n plus 2. This was a way to solve for f from Euler's formula. And therefore f minus 1 is going to be m minus n plus 2 minus 1. In other words, m minus n plus 1. So keep this in mind, that in a connected graph, the number of finite faces is m minus n plus 1, where m is the number of edges and n is the number of vertices. From there, the proof is relatively short. So assume now that we have our possibly disconnected graph with k components numbered from 1 to, numbered from 1 to n. From 1 to k components. And let's call the number of vertices in the ith component ni, the number of edges in the ith component mi, and the number of faces in the ith component fi. So what do we know about the number of faces in the whole graph? So the problem is that the infinite face is the same face for all components. So, I mean, naively one would want to say that, okay, but the number of faces of say if the graph has 7 components, you just sum up the number of faces in each component. But that's not true because the infinite face overlaps. So we want to talk about the finite faces. So let me draw an example. Let's assume that our graph looks like this. Then each of these two graphs has a finite face and infinite face, but the total graph has 2 finite faces and 1/3 face that is infinite. So I want to say something about the finite faces. Okay, so the number of faces in the total graph is 1 plus the number of finite faces. So these are the finite faces in G. And the finite faces, the number of them, that's just the sum of the number of all finite faces in each graph, because the graphs, the components are disjoint from each other, so they enclose different finite faces. So this is the number of finite faces in component number I. And if we sum over all components, we get all the finite faces in G. Now, each component is connected and planar or plane, so it satisfies Euler's formula. So remember that Euler's formula tells us that in a connected plane graph, f minus 1 is equal to m minus n plus 1. So this now applies for each component. The rest is the same. And now let's simplify this sum or just write it in a different way. So this is our sum. So 1 plus the sum of all the numbers of all vertices in all components, edges in all components, minus the sum of the numbers of all vertices in all components, plus the sums of the number 1. So the number of edges in the total graph, well, the edges come from each component, right? So the sum of the numbers of all edges in each component is exactly the number of edges in the big graph. And same with vertices, because every vertex of our graph lies in exactly one component. So the sum of the numbers of vertices across the components, that is the number of vertices in the big graph. And if you sum the number 1 k times 1 plus 1 plus 1 plus 1 plus 1, etc., then of course you get k, which happens to be the number of components. So f is equal to 1 plus m plus n plus k, minus n plus k. And if you rearrange the terms, you get n minus n plus f is equal to k plus 1 as desired. And we have proved this corollary. So this is the most general form of Euler's formula for planar graphs with k components.